Okay, so in this lecture, we'll very briefly look at uh, direct sums. Essentially, it's section 6 of R10, and well, it's a really easy section to follow, so you can read it from that as well. So, essentially, you have a vector space, and let W1, W2, Wn, these are the subspaces of the vector space. Now, what all we discussed and our intuition about linear independence, our treatment of linear independence and span of vectors translates very analogously to subspaces. Well, you can consider a vector that can be written as a sum of vectors uh, in subspaces where Wi is in the subspace Wi. So these are small w represents the vectors, and the capital W represents the subspaces. So let's assume this is true. A vector can be written as a sum of vectors where each of the vectors is a belongs to one of the subspaces. So the set of all such vectors is called as sum of subspaces or their span, and is denoted by W1 plus W2 Wn. So essentially it means that the space consisting of the sum of all these subspaces essentially means that what sort of vectors span the space. This is going to be the set of vectors which is can be written as a sum where each of these vectors belongs to the subspaces. This guy is goes to this, so on and so forth. This belongs to this. So the sum, you can check the sum, which I can denote it by, I don't know, some W. This is itself subspace of V, and we are going to be interested in the subspaces of the vector space V and what we get out of combining these subspaces, so on and so forth. So these subspaces are called independent if no sum is zero except for the trivial case. When each of these guys w sub I is equals to 0 for all I. So that essentially means that if you have a sum w1 plus w2 till wn where each of them belongs to different subspaces, and the only way this can be 0 is when each of these subspaces is 0. That means that The subspaces are independent. They don't cancel each other in any other way. So that's very analogous to, remember we did the linear independence of vectors where we had the relation C1 V1 plus C2 V2 Vn, and the only way to make this zero was to imply all these coefficients, the field scalars have to be zero. So this is a very analogous statement where the scalar has been absorbed in the field itself. So that's one of the things. And what can we say when, so in case the span is the whole space and the subspaces are independent, we say V is the direct sum of W1, Wn, and we write V equals to W1. This is the symbol for the direct sum, Wn. So the whole vector space can be constructed by this notion of a direct sum, which is the sum of subspaces which are independent of each other, and their span is the whole space. If V is W1 plus W2 Wn, and if W1 Wn are independent. So this is equivalent to saying that every vector V belonging to a vector space can be written in this particular form, W1 plus W2 Wn, in a unique way. So if W1, W2, Wn are independent subspaces of vector space of a vector space V, and if U equals to W1 plus Wn is their sum, then in fact, well, U is a direct sum. We've already seen by definition this has to be true. They are independent subspaces, and any other subspace which is spanned by these subspaces can be written as a direct sum of these guys. So these are two propositions. I'll just mention them. You should be able to show them. Well, so a single subspace W1 is independent B. Well, it's like saying a single vector is independent. You can prove its independence, linear independence. Two subspaces W1 and W2 are independent if and only if their intersection is 0. Easy to prove? Think about it, prove yourself. So that was a proposition. And proposition 2 is if W1, Wn be the subspaces of a finite dimensional vector space V, and I have a basis, so Bi is the basis for Wi, and so on and so forth. The ordered set, remember, means a particular order with no repetitions allowed. Ordered set B obtained by listing the bases B1, B2, Bn is a basis of V if and only if V is the direct sum this guy. So if this is a direct sum, then this is a basis, and if this is a basis, then this is a direct sum. Also, the dimension of this set, which is the span, is less than the dimension of these guys. And when is this equality? Well, when these subspaces are independent. Okay, so you can regard the linear independence, what we did earlier when we were considering sums like. This is a very special case of the above results where the dimension of each of the subspaces is 1. So these are linearly independent, let's say, or when we are considering single vectors, then these are the subspaces of dimension 1. And all our results are quite analogous. Okay, so there is just one more proposition to cap up this chapter, which is to say this dimension formula, which says that W1 and W2 be subspaces of a finite dimensional vector space, then I have dimension W1 plus dimension of W2 is equals to the dimension of the intersection plus the dimension of the span, the sum. Okay, so how are you going to prove it? Uh, well, essentially the idea is to first realize, I'm just going to sketch it, realize W1 plus W2 is a subspace. You can easily show that it satisfies all the properties of the subspace. 0 is an element and any, it's closed under addition, so on and so forth. And then you can actually mark its basis. So you can consider this to be the basis of this subspace. Now this basis can be extended in either direction. You can extend this basis as u1, ur, x1, x2, xm minus r. We are assuming that this guy had the dimension m and this guy has the dimension n. So this is m, this dimension is n. So now you can extend this basis and such that this is the basis set for W1, and you can also analogously extend it to sorry, I beg your pardon, let this be R. These are the R elements of the basis. So now you have wait a minute, I'm messing up my notation. So yeah, we got a bit of a notation different from the book, but yeah, so I'm just extending the bases as these guys. And so this would be a basis for W1, and this is going to be a basis for W2. These were the common things. I extended these bases. This is the basis for W2. So now all it boils down to show is that the combined thing um minus r, x1, x2, xr, y1, y2, yn minus r. So these are r, n minus r, these are r, these are n minus r, these are m minus r. That gives me m plus n minus r. So that would be, so it just boiled down to say, prove that this is the basis for W1 and W2, W1 plus W2. So that has a dimension of m plus n minus r, and the dimension for W1 intersection W2 was anyways r. So these combines to give me the dimension m plus n, which was the dimension for W1 plus dimension of W2. So how are you going to prove that this set, where the elements are these guys, which were the basis vectors for W1 intersection W2, and these guys, which was extending this to get a basis for W1 and extending this to the basis for W2, they form a basis for W1 W2. Well, you need to prove the two properties. You need to prove the span, that this basis spans these guys, and also the fact that they are linearly independent. So pretty straightforward to do it. There might be other ways to do it, but that essentially is what we wanted to learn about direct sums. So from the next class onwards, we'll start our chapter on linear vector spaces. Okay.